Hello everybody and welcome back. We're going to finish off today's paper, which is the 2004 Fryer contest. That's the grade 9 contest. And we're going to be looking at question number 4, the last question. Okay, so let's dive in and take a look. Alright, triangular numbers. This is a concept that comes up a lot on various contests. That and right angle triangles, they come up a lot too. So triangular numbers can be calculated by counting the dots in the following triangular shapes. 1, 2, 3, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The first triangular number is 1, the second is 3, the third is 6, and the fourth is 10. And the nth triangular number is the sum of 1, 2, 3, all the way up to n. Now there's a nice little formula for that you should hopefully know, if you've seen that either in a video I've done or somewhere else online, maybe even in class or in solutions to other contests. The sum of the numbers from 1 up to n is n times n plus 1 over 2. Okay. Calculate the 10th and 24th triangular numbers. That is our first question, our first task. Okay. Now, before we jump in, let's just take a look. Sometimes they tell you can use certain formulas. Sometimes they don't. So we don't know whether or not we can use the formula n times n plus 1 over 2. I think you should, because it comes up on so many contests. Nowadays, I would say yes, but this was the 2004 Fryer. They've only been doing this for, well, this is the second year of doing it. So they might not just assume you know the triangular number formula. So let's see if we can sort of derive it. Okay. So this is a nice, if you haven't seen this before, that's okay. This is a nice little trick. 1 plus 2 plus n, and we're going to write them out backwards. We'll add a little more to our example. So that's plus 3, and then this one's plus n minus 2, plus n minus 2, plus n minus 1, plus n. So counting down, that gives a 3, then 2, and then 1. So here we have the sum of the numbers 1 to n, but it's written out twice. But if you look at it, these guys are n plus 1. These two numbers are also n plus 1. 2 plus n minus 1, that's 2. And we get n plus 1, n plus 1. So we can see that 2 copies of 1 plus 2 all the way up to n is the same as n times, or n minus 1, or n plus 1, sorry, n plus 1. How many copies of n plus 1? N of them. So we can quickly rearrange and get a formula for the sum of the numbers 1 to n. Now these guys, some of the numbers 1 to n are a very specific case of an arithmetic sequence. And so the general way to add up an arithmetic sequence is done in a similar sort of way, pairing method. Yeah, so similar pairing method, but this is just a specific case for our purposes. So now we have a formula for the triangular numbers. Okay, numbers 1 to n, you get n plus 1 over n, or n times n plus 1 over 2. So 10th triangular number is 10 times 10 plus 1 over 2. And if you've ever seen triangular numbers before, you likely know that this is going to be 55. But if you want to, you could double check on your calculator. 10 times 11 is 110 divided by 2 is 55. And if you were unsure of the formula, you could actually add up 1 plus 2 plus 3 all the way up to 10. Okay? The first 10 triangular numbers, if you've seen triangular numbers enough, you just sort of know the first 10 or so. So the 24th triangular number is 24 times 25, all divided by 2, which is 12 times 25. And that should be 300. Now that one's a little harder to check, but it's still completely checkable if you want to work it out by hand or on calculator. But that gives us the 10th triangular number and the 24th, and that's what A part asked us for. Alright, 10th and 24th triangular number. Okay, B. Prove that the sum of any 3 consecutive triangular numbers is always 1 more than 3 times the middle of these 3 triangular numbers. Okay. So to get our formula in part A, we lined them up and added them up. No reason we can't do it in this part. I'll probably need a little more space than I have down here, so we'll start up here. Now I'm not going to reverse them. I'm just going to write them out. So this one's the nth. This is the n plus first triangular number. We'll put a bit of explanation here. This is a written style contest, so we should explain what we're doing. Now I know it's pronounced n plus first, but we still write n plus 1th and n plus 2th. So we get these formulas out here. So what do we have? We have 3 times, so 1 plus 1 plus 1, that's 3. 2 plus 2 plus 2, that's 2. We get 3 times the the nth triangular number plus n plus 1 plus n plus 1 plus n plus 2. Okay, and what was it the question asked us for? I think it was 3 times the middle. So I'll just write the n plus first is the middle number. So we want to get 3 times n plus 1, or the sum of 1 up to n plus 1. Now we have 3 times the sum of 1 up to n. And we could say that this is n plus 1 plus n plus 1 Now this n plus 2, he's causing us problems. But he's just n plus 1 plus 1. So we can bring these guys in here. So we got the formula we desired. The sum of 3 consecutive triangular numbers is 3 times the middle one plus 1. Well, that's exactly what we were asked to prove. Okay, straightforward enough question. C part. Oh, it looks like it will be a wordy one. Okay, the third, sixth, and eighth triangular numbers, so that's 6, 21, and 36, in case we didn't already know what those were, are said to be in arithmetic sequence. I mentioned that in I mentioned arithmetic sequences in part A. So they're in arithmetic sequence because the second minus the first equals the third minus the second. So 21 minus 6, that's 15, and 36 minus 21, that's also 15. Also, the 8th, 12th, and 15th triangular numbers, so that's 36, 78, and 120, they say, are in arithmetic sequence. So that's a difference of 42. That's what that is. Find 3 other triangular numbers, each larger than 2004, because that's the year of the contest, so that's fun. Find 3 other triangular numbers, each larger than 2004, that are in arithmetic sequence. Okay. So we're given 2 examples, and I noticed that the 8th is used in each, so I wonder if the next one maybe starts on the 15th. But other than that, I mean, that's kind of flimsy to go on. Now, what about their differences? The difference of the first one's 15. The difference in the second one is 42. That's nothing I recognize. So, yeah, there's not really a whole lot to go on. We could try an experiment, which maybe find another small example. What to do? Well, let's take a look at the general expression. We have formulas for triangular numbers, right? So maybe we can just try it out. So if we had the teeth, qth, and rth triangular numbers, and they were in arithmetic sequence, so we need the difference between the rth and the qth to be equal to the difference between the qth triangular number and the pth triangular number. Okay. That's not a lot to go on. So that's not a lot to go. We have one equation and we have 3 unknowns. I mean, what I'm looking for here is maybe some relationship that says Q has got to be double P and R has to be 3 times P plus 4, something like that, some sort of relationship. But I only have one equation and I have 3 unknowns, so I don't think I'll get a relationship like that. Okay, how about we take a look at the numbers that we're given again. So, from these 2 examples, can we find a pattern? 3, 6, and 8, 8, 12, and 15. So that's a difference of 3 and a difference of 2. So 6 minus 3 is 3, and I mean maybe these have the triangular numbers themselves are an arithmetic sequence. Maybe there's some sort of pattern between which triangular numbers. So difference of 3 there, difference of 2 there, difference of 4 there, difference of 3 there. So maybe I can get a difference of 5 and a difference of 4 in the next one. And that might narrow things down. So right now what I'm writing down is experimentation. I'm writing down my thoughts. I don't quite know how to solve the problem. But if time is called or I just can't actually get it, I can explain what I'm thinking and explain my attempt. And if I'm on the right track or I show them something interesting, I might get a mark or 2. And that could be what gives me the championship in my school or whatever. So, relationship is one word. It is not a relation and then ship. Relationship. So there's too many variables to be able to find a relationship among P, Q, and R. But that might mean that there's enough room to impose a relationship. Maybe just try and force it. Maybe say that P and Q have to differ by a certain amount. So what did we have? So let's just say that whatever the difference Q and P is, R minus Q is 1 less than. So then what do we have? We have PQR, oops, is equal to P plus K, and then P plus 2K minus 1. All right. So we could take these and we could substitute them into this formula and find a relationship between maybe P and K. We'll be down to 2 variables and 1 equation, so that should be able to give us a relationship between P and K. All right, so P plus 2K minus 1 times P plus 2K. I can multiply by 2 in this whole thing. And so that's P plus K, P plus K plus 1. And that's P plus K, P plus K plus 1 minus P plus 1. All right, so this looks a little lengthy, and we're going to get some P squareds and some K squareds and some PKs in here, but we're likely on the right track. I guess we just got to expand this out. So P squared plus 2KP plus 2kp plus 4k squared minus 2k, minus p minus 2k. That's subtract off of p squared plus pk plus p plus kp plus k squared plus k. Okay. So that's equal to, that cancels out with that. That and that cancel out with one of those. So we're left with 2kp plus 4k squared minus 2p minus 3k. So that's the first expression. Alright, and the second one, that's pk plus 1. So that's p squared plus pk plus p plus kp plus k squared plus k. Subtract off p squared plus p. So those guys cancel out once again, and those cancel out. Equals 2pk plus k squared plus k. So that's the second expression. I really hope this doesn't lead to a dead end, but I don't think so, because there wasn't an obvious approach to the problem, and this was really the only pattern I could see with the other numbers, with the given numbers, the given examples. So we know that this expression is equal to the previous one. What was the previous expression? I've already forgotten it. 2kp plus 4k squared minus... Oh, sorry, that should be plus 3k squared. Always a good idea to go back and double check things. So that canceled out there. That canceled out there. That canceled out there. Okay. So 2kp plus 3k squared minus 2p minus 3k. That's 3k squared minus 2p minus 3k. And that's equal to 2kp plus k squared plus k. Those cancel out. And we're left with 2k squared minus 2k is equal to 2p, or k squared minus k is equal to p. Alright. So these are the numbers we want. Or sorry, this is our relationship that we would like. So k squared minus k is equal to p, and we want our triangular numbers to be greater than 2004. The nth triangular number is at least as big as n. So if p is greater than or equal to 2004, then the pth, qth, and rth triangular numbers Right? And we just wanted them to be over 2004. We didn't care about anything else. We didn't want the smallest pair, right? Find 3 other triangular numbers, each larger than 2004, which are an arithmetic sequence. So we don't care. They could be over 1 billion. As long as they're over 2004, it doesn't matter. We're not asked for the smallest set. Okay. So, we need to pick a k value, which will be the difference between the pth and the qth triangular number, or the difference between p and q. So what k value gives a p greater than or equal to 2004? Well, we want what value of k would give us equal to 2004? There's a quadratic formula, so we just do negative b. Negative b is 1, not negative, so not k. So k equals 1 plus or minus, but we'll only use the plus side, b squared minus 4ac. So that's 4 times 2004 all over 2. So we'll likely get some weird number. And then we'll be able to take the next highest k value. That should do it. 8017, does that have a square root? We can just check on our calculator. It's not one I have memorized if it is. No, it's about 89. We want a positive k value is my point. Because k is the difference and q has got to be greater than p. So this is approximately 45. So it's 45.26. So we're going to try k is equal to 46. P is equal to k squared minus k. 46 minus 46. 46 times 46 is 2,116 minus 46. That's 2,070. That's p plus k. So we're going to be looking at the 2070th triangular number. The 2,116th, so q is k squared, I guess. And r is q plus k minus 1. Where was I? Oh, yes. Plus 45. 2161. Now, I got distracted there for a moment because p is k squared minus k. That's fine, but q should then be k squared minus k plus k, which should be k squared. So this q is a square, but our other examples were the middle number was not a square. This is not a square. This is not a square. So, I'm a little confused. Just a little bit. I'm wondering if one of these expressions I did wrong. There it is, yeah. So bring the k squared over here, that should be 2k, but this should be minus. So minus 3k minus k, that should be minus 4k. Alright, so we're going to have to redo the quadratic formula and everything. Shouldn't be that bad, but it's important to check, and it's important to make sure your numbers make sense. My q was a square, and it came out because it was k squared minus k and then plus k again. Basically, we just need to redo this whole thing. And so it struck me, hey, I didn't see a 9 or a 4 anywhere in the triangular numbers that we were given as example. So what gives? So we're going to need different k values. 46 will probably still work. I don't have to explain the quadratic formula as much this time, so that's 2 plus or minus square root of 4 plus 4 times 2004 all over 2. We still want the positive value. 2004 times 4, 816. I'm pretty sure that is not a square either. It is not. It's still, well, 89.5 basically. And I've just completely gone off on my spelling. I want the word want, not the word won't. Sorry about that. That's my arithmetic mistake. So that should be approximately, so that plus 2 divided by 2. Yeah, 45.7. So it really didn't change a whole lot. But we tried k equals 46. We're going to get different p values and everything. We can just clear this page. K squared minus k, so that's 46 squared minus 2 times 46. 46 times 46, that's still 2116. Minus 46 minus 46, that's 2024. So that's still greater than 2004. Q is p plus k, so that's going to be 2070, because that was our previous value. And R is k plus, or p plus k minus 1, 2115. And you'll notice that is 1 less than a square, which should track, so 8 was 1 less than a square, and 15 is 1 less than a square. So this is starting to look a little more correct. We still need to actually figure out what these triangular numbers are. P times p plus 1 over 2, well, let's work that out. So that's 2049300. That's definitely greater than 2004. So the next one, Q. That's 2143485. And the last one, 2115 times 2116 divided by 2. Get 2237 670. What's the difference between the rth and the qth? 2143485. So that should be a difference of 94,185. And if we add that to the one for P, we get exactly the value for Q. What was that difference again? 2237670 minus 2143485. Those guys are over 2004 and in arithmetic sequence. Fantastic. And we have written out the actual numbers in case they wanted them. So these numbers are likely not the smallest. We just wanted the triangular numbers over 2004. We didn't want their position to be over 2004. So there's likely a bunch of smaller ones. But that r square, or that r triangular number minus qth triangular number equals qth triangular number minus pth triangular number. That seems like a very interesting equation to deal with. You can't really, there's no relationship amongst the p, q, and r that is immediately available just by looking at that equation. There's too many variables, and three variables for one equation. You're not going to get really a relationship amongst the three that always works and gives every possibility. Now, I did a little computer program to spit these out, and there are dozens, and they don't follow a pattern. There's so many arithmetic sequences of three triangular numbers. So if you're into computers, and it's grade 9, so you might not have seen that sort of stuff, but if you know how to program a computer, try and get a whole bunch of possibilities, work them out. I have yet to find really sort of a cap that says there's only so many for a given number. So like the 1, how many arithmetic sequences of triangular numbers can 1 belong to? Is there a limit? I don't know. I wasn't able to work that out. But there's no sort of set list with a given pattern. There's a whole bunch of patterns in there. And we just picked one. We said, let the difference between the first two, let the difference between P and Q be 1 more than the difference between Q and R. That's all we said. We just noticed that pattern. But there are so many more. There's so many answers you could have for this question. The problem is, how do you justify? How do you arrive at your solution? I think we did a pretty good job. There was admittedly a problem there when I got the wrong formula for P, but we noticed it and we worked back and we found out where the problem was and we got a good answer. As I say, so many other answers to this arithmetic sequence of triangular numbers. You should be interested to know I've yet to find one that has 4 triangular numbers in arithmetic sequence. I don't think it can be done, and if you're interested, if you're so inclined, a challenge for you would be to show that that can't work, or find me an example where it does work. That'd be something to do. And if you can't show it can't work or find an example of it does, please feel free to leave it in the comment section down below. And I liked this question. If you liked it too, throw a like on the video. But that's the 2004 Fryer paper, and yeah, that's about it. I'll see you guys in the next contest, whatever and whenever that is.